Hi, my name is Austin Cox and this is Homework 1, Part A1. So here we have a cylindrical tank that has finally reached steady state after having some initial volumetric flow rate coming in for a long period of time with some volumetric flow rate going out. So here we will be deriving a differential equation for the height of the liquid level of this tank. So to start, we will use our Bernoulli's equation for our energy balance. So that is our injection work, P2 minus P1 over rho for density plus gravity times Z2 minus Z1 plus our difference in velocities squared over 2, and then our energy balance is going to be equal to 0. So to simplify our expression here, we need to pick 2 points in our system. We can pick our points being 1 at the top and 2 at the bottom. So with our 2 points that we picked, our P1 and P2, our pressures will be equal. So this term will go to 0. Next we move to our potential energy term where we have Z2 minus Z1. So if you look at our 2 points we picked, the differences in our heights is actually going to be our height. Or the differences in our 2 points is going to be our height, h. So there is our h, and since it is going to be Z2 minus Z1, we need to negate our h value. Moving to our kinetic energy term, our V1 is 0 since we have some constant volumetric flow rate. So simplifying this, we can go 0 is equal to negative GH plus V2 squared minus 0 over 2. Simplifying this, we can get V2 is equal to root 2GH. So here we have solved the expression for our average velocity of the outlet of the tank. Now we can plug this in by multiplying our velocity times the cross-sectional area of the hole of our outlet to get our volumetric flow rate out. So our Q out is going to be equal to A out times root 2GH. So now that we have an expression for our volumetric flow rate out, we can go ahead and set up a material balance for this scenario. And we will be doing that by calculating the volume of the tank, and the amount of the water in the tank is going to be equal to the cross-sectional area AC times our height So that is for the amount of water in our tank. However, that is going to be changing with respect to time. So we'll add that. And for this specific scenario, we will have a constant cross-sectional area, so we can go ahead and pull that out. So we will get AC times DH dt. All right, so next we will need to move on to the right side of our equation for our material balance, and that is going to be equal to our flow rate in minus our flow rate out. So we will have AC dH dt equal to Q in minus Q out. And we had solved for our value of Q out, and we have that here. So we can go ahead and plug that in. All right, so now that we're here, we can go ahead and divide our right side by AC to just be left with our dH dt. Alright, now that we have a separable differential equation, we need to look at our dependent variable to determine if it is nonlinear or linear. And here our dependent variable is height, and our height is inside the square root. So our h is to the 1/2 power, therefore telling us that it is nonlinear. So next, we would need an initial value in order to solve this problem. However, for this scenario, we are declaring that we are at some steady state for some amount of time. However, at time equals 0, we're going to increase the flow rate, and then we will be running a simulation using Euler's method on Excel to visualize that. So in order to do so, we need to find the derivative of our dH dt. And we know that that will be equal to 0 due to having a constant flow rate in. So doing so, we have dH dt prime is going to be equal to 0, and then that will be equal to q in minus a out root 2g and h. So here I'm going to add and do some massaging in order to pull some value for our h in terms of our expression here. So we'll have a out root 2gh is equal to q in. So I'm going to have h to the 1/2 is equal to q in over our a out times square root of 2g. So our h is to the 1/2 power, so we can go ahead and square both sides. So now we have an expression for our h value. And from here, we need to go ahead and discretize our dH dt in order to solve it using Euler's method in Excel. So to do so, we need to come back up here and solve for just our delta h. So we will have delta h over delta t is equal to our 1 over AC times our volumetric flow rate in minus A out root 2GH. And then we will just be wanting to solve for our difference in height, our delta H. So we'll have delta H is equal to the volumetric flow rate in minus our flow rate out. And that will be divided by our cross-sectional area, and then we will be multiplying by our delta T. All right. So here is our discretized expression for our differential of height for the liquid level in the tank. And from here, we will be taking this to Excel and simulating it there. Now that we have derived the differential equation in which it describes the height of the liquid of the tank over time, we will now simulate this response in Excel using Euler's method to run the simulation. So I'm going to enter into Excel. All right. So now I'm going to define some of our variables. So we have AC, our cross-sectional area is 1 meter squared. Out. Second. Next, we can define our dt, and for now we can just make that 0.001. That's going to be seconds. We need to define our gravity G. I mean 9.81 meters squared per second. And then next, we need to define our H naught. It's going to be equal to our Qn naught over the square root G. For this simulation, we can go ahead and start counter for our iterations using Euler's method. So we do that. Series almost steps. We need our p value, or differential time step, times step number. Each value is going to be equal to h naught. And our second one is going to be equal to this value plus what the dh is equal to. So we need to create our differential of height equation in this column. And then that is going to be equal to dt dividing by to be equal to h naught plus our dh. We have our values. We can insert a scatter plot, plot against our height. To isolate all of our 100 values, and this will be equal As you can see here, our time values versus our heights, it is remaining at steady state. And that is because we have not yet changed our Qn naught value. We have remained at 0.1 for a very long time, and this is visually demonstrating that. So now that we have accomplished steady state, we need to go back to our assignment, and suddenly at time equals 0, the inlet flow is increased to 0.15. So let's add a new Qn, that is 0.15, and that is mt per second. Just our differential height expression to now hold our Qn naught value, which is not defined yet. You can see that we are starting to have an increase in our height over time. Let's go ahead and change our dt to 0.003. We see more of a rapid slope. Can't really visualize that curve that well, so I'm going to increase the number of time steps. Solving the differential equation for the varying height of the liquid level of a tank. Now moving into Google Collaboratory to show this simulation using Radau's method using Google Collaboratory, be repeating our previous work now in Google Collaboratory involving solving the differential equation for the liquid level and our height across varying volumetric flow rates. So to begin, we need to import our libraries. So first we can import numpy as np. Next, we want to go from and solve IVP function in order to solve our initial value problems. We can go ahead and start defining our parameters. And for that, I am going to go back to our Excel sheet so that I can get our AC is equal to 1 meter squared. A out is equal to 0.2 meters squared. dt, due to not doing it the calculation by iterations or steps, we will be using a more robust method. So we can go right into G is equal to 9.81 meters squared per second. So now we can go ahead and define our function. Define dh dt, dependent variable, followed by our dependent variable height. And then for our function here, we will be wanting to include a new volumetric flow rate n. And from our problem, we have a value of 0.15. To return right hand side of our dh dt expression that we had derived on the whiteboard. So that is going to be Qn minus the Q out of the tank, which is A out times NP square root G times RH, and then all divided by our cross-section area. Shift enter. So now that we have returned our right-hand side of the function, we are going to want to solve our initial value problem. So the result of our initial value problem is going to be equal to solve IVP, and then our function here is dH/dt. Next is our time span. So we are going to be going from 0 to t end, which means we also need to include a t end, and we can just make that equal to 10 for now. In our solve IVP function, we need an initial guess. So for this, we can just do we can do a list of our h naught values to include um, the y or the height initial value across, and then we'll be including that across our steps. So after our initial guess, our method here is going to be equal to Radau. Lastly, its output equal. Let's retry that, taking out some coding syntax. So let's go ahead and check our res. So the solver successfully reached the end of the integration interval. We have our values for t, y, and we have a solution. Full screen. When we have solutions, we can go ahead and create some plots. And to begin that, we need to create some values for our x and y. So our x is our t. So we can go t plot is equal to np dot linspace, and this creates a list of numbers for us. And here we are going to go from 0 until t end, and then our num 201. Shift enter. Let's check out this t plot. Here is our t plot values. Now we can plug our t plot array into our solution that we got right here. So we can do that by saying res.sol for the solution, and then we're going to evaluate that across the array of t-plot. Shift enter. So here are our heights solved across these times. However, this is a 2-row array, so we will need to repeat that res.sol of tplot, and we're just going to want the first row. So for the first row, the index of that is 0, and we can confirm that we succeeded by only having one bracket. So here is our array of our heights. So now we want to bring this to our plotting cell, and we can call this hplot is equal to paste that in, enter. So now that we have our x and our y values from our time and our height, we can go ahead and add our plots. So we can go fig is equal to make subplots. And
differential height against our time. So you can see that it is slowly ramping up and finally curving off. And this is similar to our curve from Excel, which was solved using Euler's method. However, using Google Collaboratory and the Radau method, this is a more robust method and gives us more insights on these scenarios. Thanks.
Hi, this is homework 1, part A2, in which we have 3 tanks in series similar to our previous part A1, in which we have a flow rate in with a flow rate out. However, here we will be adding it to a series of tanks. So now I will be deriving our differential equations for these tanks. So for our first tank, we will have our differential of height with respect to time is going to be equal to 1 over the cross-sectional area. And for this situation, we are going to go ahead and assume that AC1 is equal to AC2 is equal to AC3. And that is just declaring that all 3 of these tanks have a uniform cross-sectional area, as well as we can write out 1, out 2, and out 3. So that's just keeping it simple with a uniform cross-sectional area for our tank. So continuing with this, it will be our Qn from our first tank, and then it'll be minus our Q out from the second tank, and from our previous part, we know that that is going to be equal to the area of the outlet hole times the square root of 2GH1. And here we can go ahead and label our heights in their respected tanks. And then we will be continuing this through. So dH dt is equal to 1 over AC times Qn. Got carried away there. So for our second tank, our inlet will be our outlet from the first tank. So we will have A out times 2GH1, and then this will be subtracting our outlet flow from our second tank. So A out times 2GH2, and then for our third tank, our dH dt is going to be equal to 1 over AC times our outlet from our second hole, which is going to be our inlet into our third tank. So A out times 2GH2 minus A out times 2GH3. Alright, so now that we have our 3 differential equations, we need to define what our Qn is going to be for this scenario. And for this problem here, we will be going to be using a proportional controller. So we can define that as such. So we will have Qn is going to be equal to Qn naught plus Kc times our height set point minus our height. So here is our expression for our Qn, and we are going to be using our Kc here, which is defined as our controller gain, and we will be using Google Collaboratory to implement these expressions and to determine what the optimal value for our Kc is, in order that we have steady and continuous oscillations that are neither growing nor dying out. Alright, now that we have derived the 3 differential equations for the 3 tanks in part A2, we are now going to be implementing this into our code for Google Collaboratory. using this new Qn naught value and utilizing the controller gain Kc. And in the end, the set point of the third tank is going to be 20% higher than the initial steady state of the third tank. And now we will go into Colab to simulate this. So here I have the previous code. I can go ahead and clean some of this up. And I can go ahead and update this plot as well. You can do that by saying fig dot update. We're going to be updating the layout, and that is going to be equal to, and we can make our width equal to 600 and our height equal to 400. Let's go ahead and run all. Delete these as well. So now we need to update our Qn for this new simulation that we want to run. And from the previous derivation, we know that this new value is going to be equal to Qn naught plus Kc. And then this is going to be times the height set point minus height. Okay, and now we need to go up here and add our Kc. And again, that is our controller gain. So for now, I'm just going to start that off with an initial value of 10. Also, in this, I'm going to unpack the height set point minus h. That is going to be our error. So we can represent that with an e. So we can do e is equal to h sp minus h. And then we can change this to times e. Equation, we have an undefined variable, our height set point, and that is going to be equal to 20% higher than our initial state. So 1.2 times h naught. Shift enter, shift enter. And here we have our new plot with a Kc value of 10. I'm going to go ahead and combine some of these, paste that in, and delete this. And then I'm going to do the same for this. Paste that in. And obviously I want to combine this. And I'm doing this just so that I don't have to hit shift enter that many times. Let's recheck this. Awesome. So now we have updated our initial value, and this is just for one tank. So now we will need to create a function for our 3 tanks. So we can define that. Define, we can call this 3 tanks. And our independent variable here
is going to be time again. And however, for this scenario, we have three tanks, so we will have um, three different values or three heights for our dependent variable. So we'll need to make that a vector, and then we make h1, h2, and h3 equal to vec. I'm seeming to have an issue with a 3 in front, so let's just call that right hand side 3 tanks. All right. Next, we need to bring our qn value from our previous function. Here to paste it. All right. And we'll need to change this to h3 because we are basing it off of our third tank height. So next we can go in and enter in our value for our Q1, Q2, and Q3 out. And this is our volumetric flow rate out of the tank. And we are going to define this as the sectional area of the outlet hole times the velocity of the outlet, which we previously had defined, and we know that it is this value here, the square root of 2gh. So I'm going to select this here, Control C, Control V, and we'll need to update these h's for h1, and then we're going to do the same thing for h2 and h3. Okay, h2 and h3. Awesome. So now we need to finally update our return function now that we have kind of unpacked the outlet for the Q1, Q2, and Q3, or we have unpacked the volumetric flow rate out of the three tanks. That way we can eliminate that, and then we will do Q in minus Q1 out divided by AC for our first tank. All right. And then for our second tank, we are going to have Q1 out minus Q2 out. And then that is going to be divided by the cross-sectional area again. And then lastly, for our third tank, we are going to have Q2 out minus Q3 out. And then divided by our cross-sectional area, AC. Shift Enter. So now that we have defined our function and returned the right-hand side, we will now want to go back to our previous code and select this, and then come down here and paste it in. All right, so in our solve IVP function, we will need to update our function name, and we have declared it right-hand side, 3 tanks. Our time iterations, we will still be going from 0 to t end. That way, if we ever want to change the duration of the simulation, we can easily go in and just update that value. Next, for our initial values, now that we have 3 tanks, we will now need to have 3 initial guesses, and we can do that by having three um, three value three values listed here for h naught, and those are lists of values being solved through the differential equation.
right? Okay. T-plot or for our x values is going to remain the same since we will be using t-plot for all three of our plots. However, we will need to update our y values for our h-plot now that we have three tanks. And we can do that by declaring h1 plot, h2 plot, h3 plot, and this is going to be equal to the result function that we have here, evaluated at the solution that is solved, and then of the x values from our t-plot. However, now that we have three tanks, we do not need to call for the first row since we have an array unpacked in our vector. So now we need to add our scatter plots for the tanks. So we can name this one equal to h1. And then I'll copy and paste this a couple times so that we can get h2 and h3. Right? h2, h3. Let's give this one last look over. Oh, I need to update my y values. h1 plot, h2 plot, h3 plot. Enter. Let's see what we got going on. So, as you can see, with a Kc value of 10, our tank is shooting all the way up for our height 1, and then moving on, and then finally reaching. So now, in this part, we are now going to try to obtain a value for the controller gain such that our oscillations are never ending and they are never growing nor neither dying out. So let's go ahead and try doubling this. Enter. All right, so now you can see that they're starting to move further along our x-axis. And again, we are trying to reach a height set point in our third tank of 20% higher than our H naught. So let's increase this to 30. Okay, so now we can see that our oscillations are growing. So we'll need to lower our Kc value so that we do not find these values growing. So let's try 29. Wow, that looks pretty nice. 0.22. There's a little bit of a deviation. Let's go 29.125. Okay, 0.229, 0.231, 0.231. Okay. All right. So I think we have completed this homework. Part A, we have attained a steady oscillation where the plot is neither growing nor shrinking. Thank you.